Sound on. Okay, if everybody could grab a seat, we'll go ahead and get started. We need to proceed relatively quickly so we can get through everything. And hopefully by this afternoon, you can go directly from this to Aki's model selection talk. Anyway, this is the tutorial on hierarchical models. It'll be spread out over 2 sessions with a coffee break in between. Before actually getting started, I have to say this, otherwise I'll get fired by Columbia. I work at Columbia. Columbia develops Stan. I use Stan as part of a personal business and as a result that results in the appearance of a conflict of interest that you should be aware of when listening to this presentation. So what are we going to cover? Like I said, we have 2 sessions, and the first one, we want to talk about conditional distributions, the building blocks for hierarchical models. So we want to think about conditional distributions, which are really the essence of hierarchical models. We want to practice writing functions in the Stan writing some simple Stan programs that do hierarchical modeling. So for those of you who have your laptops, be good to get them out. Hopefully you've already installed rstan and you can do some things. We'll also, toward the end of the first session, estimate a hierarchical model using rstanarm Glimmer. I don't know what happened over there. Read the one on the side. Okay. And we'll do a hierarchical model with rstanarm. In the next session after the coffee break, we'll get into brms and writing some hierarchical Stan models on our own in the Stan language. All right. So to get started, I want to think about some hierarchical data generating processes. Here you can assume the parameters are known, but think about data that might be generated in 1 or 2 or 3 or 4 steps. So one of the examples I like to use with students is to think about modeling bowling. So how many pins does person I knock down in 2 rolls of a frame of bowling? How might we think about a model for something like that? Can bowl this thing? How many pins was that? 7. All right, so if I knock down 7 pins on my first roll of a frame of bowling, then what sort of a model would I need for the second roll? Right. So there's going to be only 3 pins left. My model would have to take that into account somehow. So I have some probability distribution that might give me the probability of knocking down 7 or 4 or whatever it may be pins on the first roll. And then 10 minus that number is the available pins to knock down on the second roll. And my model should have to take that into account somehow. It wouldn't make sense to have a model where there was some positive probability of knocking down 12 pins on 2 rolls of a frame of bowling. So the second roll has to take into account what happens on the first roll. And in our code, it might look something like this. So you're going to need 2 probability distributions, one for the first roll of a frame of bowling, and then another probability distribution for the conditional probability of knocking down some number of pins on the second roll of a frame of bowling when there's only 10 minus x1 pins available to be knocked down. So the second is a conditional probability distribution. It depends on the realization of what happens on the first roll of your frame of bowling. And in our code, we might do something like this, just sample uniformly from the integers between 0 and 10. That's our supposed first roll. Subtract that from 10 to get the number of pins left. Do similar thing, but with a different upper bound for the number of pins you knock down on the second roll. Add those together, and that's the number of pins for a knock down those number of pins over 2 rolls of a frame of bowling. And really, Stan is doing a more complicated setup than this, but all it's doing is drawing from a conditional probability distribution that you define. And it's natural to use hierarchical structures in defining that distribution that Stan is drawing from. But a lot of times with data or with parameters, we have this idea of an ordering to it, that first there's a distribution for something, and then second there's a distribution for something else that depends on the realization of the first random variable. Just like in bowling, the second roll depends on what happens on the first roll. The number of pins available to be knocked down depends on what happens on the first roll. So you might say bowling is not very interesting. You might be right. But we could think about a generative model for something that could be estimated by instrumental variables, or what frequentists often use, two-stage least squares. It's really the core model or estimation method used in microeconomics. And this goes something like this. So we're going to have a 2x2 covariance matrix for the errors. And we have 2 different outcomes that we're going to be modeling: a treatment variable and an outcome variable that's ostensibly a consequence of our treatment variable. So we have 2 error terms. We might think that they have a bivariate normal distribution with mean vector 0 and some covariance matrix that consists of squared standard deviations along the diagonal. And in the off diagonal, we have a covariance, which we're representing here, with a correlation rho multiplied by the standard deviation of the first variable, sigma 1, and the standard deviation of the second variable, sigma 2. And consequently, we have distributions from which describing our beliefs before seeing the data about sigma 1, sigma 2, rho. In this case, we just used uniform for rho and some exponentials with some rate parameters for these 2 standard deviations terms that we are going to want to be estimating. And then toward the bottom, we have 2 equations that give us a model for the treatment variable t, which is a function of some control variables x and a so-called instrument z. And then at the second, well, it's really all the same stage, but the second equation there, we have some outcome, which is also a function of the control variable, but instead of being a function of z, it's a function of t. So we have beta 2 being multiplied by t, but t is the variable that we're modeling in the first stage of the process, and consequently we need to have priors on the alphas and the betas. These could be trivariate normal, they could be independent normals, they could be really anything, just for the coefficients on these 2. So if we go through this generative model, draw from exponentials and uniforms for the bivariate covariance matrix for the errors, draw errors for each of our observations one time, draw the alphas and the betas from these multivariate normals, use the realizations of the alphas and the error nu to give us a realization of t, the treatment variable, and then use that realization of the treatment variable along with our control variable x and the realization of epsilon that we drew to form the outcome variable y that we're interested in. And so if we go through these steps, we generate data through this process that mirrors that of bowling. Instead of having rolls in a frame of bowling, we have a first step where we draw a realization of the treatment variable, and then a second step where we draw a realization of the outcome given the treatment variable whose realization we obtained in the first stage. And so this model is also a hierarchical model for a data generating process with 2 outcomes. the treatment and the ultimate outcome of interest. But really, it's just a more complicated example of bowling. You know, there's priors and there's parameters and stuff like that. But at the essence, it's still this two-step process. Get the realization of treatment, get the realization of the outcome, given the treatment variable. And we want to generalize this from thinking about these, you know, two-step distributions just for data, but to apply it in the same way when thinking about priors on parameters in our models. Questions so far? Give me an opportunity to throw this thing. Sounds like a lot of fun. Yes? No!
Could you just give like a practical example of what T and Y might be?
A good example of this in like microeconomics is to think about treatment as the number of years that you go to school, and the outcome as your sort of lifetime income or your permanent income. And the main task is to estimate beta 2, which is the sensitivity of your lifetime income to the amount of education that you invest in. Now that is a little bit complicated because of this correlated error terms, and frequentists have a variety of ways of dealing with that. You can do it in a Bayesian context as well, but we sort of think about these two outcomes, or maybe one intermediate outcome and one ultimate outcome. Intermediate outcome being years of schooling, ultimate outcome being some measure of success in the labor market given the amount of investment you have in schooling. Thank you. Other questions? All right, so those of you who have Stan open or our studio or whatever your preferred editor is, let's think about writing just the end of a Stan program. I've already given you the data block and the parameters block, where we're going to think about a model for does someone vote in an election? Or if you're from a country that has basically everyone votes, you know, do you vote for the Liberal Party or the Conservative Party? You can maybe combine those two into a two-step model like bowling, but for now let's just think about the probability that someone votes in a logit model. And we have two predictors, the age of the person and the income of the person. And so that would be pretty straightforward. One here is the coefficient on age. We want to make that a linear function of the person's income. So this might be a model where we think rich old people behave differently than poor old people. But we want the coefficient on age to be a function of the person's income. And so linear function, that's going to have an intercept and a slope. So in the data block, we have the number of observations, vectors for the explanatory variables age and income. The outcome variable is just 0 or 1, success or failure, whatever you want to think about the outcome as being. And then in the parameters block, we're going to have two vectors of size 2. Let's say lambda 1 is going to contain the intercept, lambda 2 is going to obtain the slope for the coefficient on age. And then beta 1, beta 2 is going to be the overall intercept and the coefficient on income. So in our model block, we want to write out a structure where the coefficient on age is equal to lambda 1 plus lambda 2 times the person's income. Then we want to multiply that coefficient by the person's age, add it to beta 1 plus beta 2 times the person's income. We'll get the log odds of voting, and we can put that into a logit model likelihood. So I'll give you a few minutes to work on that, but this is basically the same thing as having an interaction term between age and income. So hopefully everybody at least got a chance to make a start on something like this. So here's what we were looking for. We want to define a local vector, beta age, which is the coefficient on age. And it's going to be a function of the person's income. So it has a slope, lambda 2, has an intercept, lambda 1, multiply lambda 2 by the person's income. Income is a vector of size n, so this is going to result in a vector of size n, which is going to be our coefficient on the age variable in this logit model. Then we want to take beta age, which is a vector of size n, and we want to element-wise multiply it by age, which is also a vector of size n at the end there. And then beta 1 plus beta 2 times income is added to that, and we get the log odds of success, eta. And then we can use as a likelihood the Bernoulli logit log of the probability mass function for the probability of voting given their log odds of voting. And so maybe you didn't come up with exactly that. There's more than one way to do it. This is the way that fits on the slide. Of course, you should also have priors on lambda and beta. There is no sigma in this model. That's a mistake. But on lambda and on beta. But those are pretty much up to you. But the point that I wanted to get across here is we have another bowling situation in disguise. We have an expression for the coefficient of age, namely beta age. So we set that, and then we use that on the next line as part of the expression that goes into the log odds of success in this Bernoulli logit model. And so we have basically income influencing the probability of voting in two ways. Directly via beta 2, and maybe somewhat indirectly by its effect on the coefficient on the age variable beta age. And so this is the sort of thing that you might want to use in some of your STAN programs. If we can make this even better as we go along. But before we start to do that, are there any questions about the bottom 3 or 4 lines here? Yes.
Thank you. Why is at the bottom? Why do you dare use the target plus is? You could do what? Be something non-obvious. Be careful.
Yes. So do I have some chalk? No. Okay, so imagine I had chalk. The target plus equal is essentially equivalent STAN syntax to vote tilde Bernoulli underscore logit parentheses eta. It results in essentially the same STAN code. The syntax that you're referring to was sort of the syntax that STAN started out with in 2011. We added this a few years later, but it implies the same likelihood.
Thank you. Just by error, I think I had another coefficient in front of beta 2 times income. What would happen if we do that? So we had another independent, like for the eta one, like we had, we would probably put beta 2 in front of the beta h, and then.
Oh, so if beta had been of size 3?
No, actually, so beta 1 plus beta 2 times, and then beta h.
Oh, so this, the top line in the model block is really just the sensitivity of the log odds to the person's age. But we're saying as part of this model, that sensitivity depends on the income of the person. And so this might correspond to a theory that poor people who are elderly have different voting behavior than richer people who are elderly. Or conversely, younger people who are rich have different behavior than younger people that are poor, etc. And so this is really just in the top line there, establishing an expression for what's the coefficient on age, and everybody has their own coefficient because everyone has a different value of.
Right. I also see the case we have for eta quadratic term if we expanded it.
Yeah, and we'll get to that next.
Okay.
Question?
Thanks. Why it is in the model, in the first line there is a multiplication, and in the second line there is a also dot multiply?
Oh, why is there a dot here?
Yes.
Yeah. So this is the dot star is the syntax for element-wise multiplication. We have a long vector of size n for beta age and a vector of size n for age, and we want to multiply them together. The regular star, this is scalar times vector, and so it has a different notation. Other questions? Any questions in the back? I don't know how far I can throw this, but all right. So as was pointed out a second ago, this is really essentially equivalent to an interaction term. So if we have eta is this function of income and age, but the coefficient on age is specific to each person rather than one coefficient that is common to all people, and that coefficient beta 3 I is equal to lambda 1 plus lambda 2 times the income of the ith person. And then if we just substitute those that expression for beta 3 and then distribute the, distribute the age term, multiply it by income, multiply it by the coefficient, we get this expression on the line here, which you can hopefully see there, right? And then if we wanted to, we could use some frequentist method to get unregularized estimates of beta 1, beta 2, lambda 1, and lambda 2 by doing income plus age plus income colon age. So we're going to be estimating 4 parameters there, and then family equal binomial to specify that this is a logit model. So what we did before with our Stan model was giving us an equivalent likelihood function to what we could do just on our own in R with interaction terms. The Stan version, I think, is easier to interpret because it makes it explicit how we believe the coefficient on age is formed. Whereas if you just do, beta 1, beta 2, or income, age, income colon age, you get out these coefficients that are notoriously difficult for beginners to interpret because you have to think of one, when the other one is 0 and stuff like that. With Stan, we could just get the posterior distribution of all these quantities of interest. So doing it in R with GLM is certainly quick. Doing it with Stan, I think, is easier to interpret, but it takes longer to write out. And the thing about this idea with interaction terms is that many of the hierarchical models that are specified in the literature are really just models with interaction terms between some predictor and some group level dummy variables, like what country do you live in, or what groups do you belong to, things like that. Interacting age variable, income variable, etc., with these group level dummy variables. And that's not all of hierarchical models, but that's a lot of hierarchical models. And so we want to spend some time this afternoon talking about that very important case, but it's a more general idea of, let's get an expression for something and then let's use it in our expression for something else. Just like bowling, just like two-stage least squares, just like interaction terms, is all have a common logic behind them. So now let's make our Stan program a little bit different. What we previously wrote said that the coefficient on the person's age, as to their log odds of voting, was an exact linear function of income. There's lambda 1 plus lambda 2 times income. There's no noise in that relationship. So knowing the person's income, or if you have two people with the same income, then they're going to have exactly the same coefficient on age. And that may be more restrictive than what we think is reasonable. So now let's modify our Stan program that we wrote before so that the coefficient on the person's age is a noisy function of the person's income. So just because two people have exactly the same income doesn't mean they have exactly the same sensitivity in terms of the log odds to the age. So what we had before, it's the same in the data block, but in the parameters block we have two additional things. One is the noise, which is a vector of size n, which is the noise in the sensitivity of age to voting, and sigma, which is going to be the standard deviation of that noise. So sigma is just a scalar. We've restricted it to be positive because it's a standard deviation. And so sigma controls the amount of noise relative to the signal in the coefficient on the person's age as to whether they vote. So really we just need to change a couple lines of the Stan program that we wrote a second ago in order to generalize this and maybe make it more appropriate to a situation in which it's not an exact function of the person's income, but just kind of a loose function, a noisy function of the person's income in terms of how that affects the log odds of voting through the person's age. So I'll give you a few minutes to make that modification. Everybody got it? I'll take that as a yes. So I've modified the first line here, lambda 1 plus lambda 2 times income. That's the same as it was before. But now I have plus the noise scaled up by its standard deviation, sigma. And this is an example of a non-centered parameterization. This is a point we'll come back to several hours from now after the coffee break. This idea of centered versus uncentered parameterizations that you can do with things in the location scale family, such as the normal distribution. But really all I've added on here is the scaled noise term going into the coefficient on beta age. The next line is the same as it was before, beta 1 plus beta 2 times income plus the coefficient of age times age. That constitutes the log odds. That goes into a Bernoulli-Logit log PMF. And now I have one more line where essentially I've said my prior on the noise, normal 0, 1. But if noise has a standard normal prior, then sigma times noise implicitly is going to have a prior normal distribution with mean 0 and standard deviation sigma. That's just taking advantage of the scaling property of the normal distribution. So I can say noise has a standard normal distribution, or I can say scaled noise has a normal distribution with standard deviation sigma. It implies the same thing, although sometimes Stan, it's easier to sample one way or another, and we'll talk about that, like I said, later when we get into efficiency. But here we're mostly just worried about concepts, but we've sort of introduced this new concept where our interaction terms don't have to be exact relations. They can now be noisy relations. And that might more appropriately describe some process that you're interested in modeling, whether there's measurement error in the data or any number of other reasons. You might think your parameters have some amount of noise in them, and you want to estimate those along with what's the standard deviation or what's the variance of that noise, of that measurement error in some of these processes. But it doesn't even have to be measurement error. We don't really measure beta age directly, but we can specify structures like this in a Stan program and estimate sigma along with everything else as part of our joint posterior distribution. And that, whether you immediately have ideas to take advantage of that or not, it's a pretty cool thing. I mean, we saw before that we could just do these interaction terms which have exact, linear relationships. Some coefficient can be a function of another one. But adding the possibility that it doesn't have to be a perfect linear relationship anymore certainly expands the scope of things that we might be able to apply a technique like this to using Stan. And this is not something that has a simple equivalent with like GLM or something like that. Those also assume exact relationships. Questions about that? Yes.
Okay, does that mean with this type of modeling that you can have a linear relationship taking into account heteroscedasticity or something like that?
Right. So if we wanted to, so essentially we have heteroscedasticity in a coefficient. We have extra noise in the coefficient on H. A more typical way to use the word heteroscedasticity, there are not that many typical ways to use the word heteroscedasticity, but the most typical one would be you have some variance or some standard deviation of the error terms, and you want that to vary from one unit of observation to the next. And it might be a function of some, will have more noise than others in estimating it in an unstructured way. All of those things, fairly easy to do with a Stan program. All of those things are basically just a slight tweak on the ideas that we've already been talking about this afternoon of, write an expression for this variance, showing how it's, bigger for some people than it is for others, and then estimate that, or allowing for the possibility that it's bigger for some people than for others, and then to go to estimate that with the Stan program and find out what the sensitivities and who has more variance and why. All those are sorts of things that you can attack using Stan and using hierarchical structures. All right, so let's get to it. So moving in the direction of a more typical hierarchical model, where typical means often used by frequentists. So the classic example of this, you might think, something along these lines. We're going to do a study. We want it to be, our study to be representative of the country as a whole, but it's way too expensive to give tests to like all students or something like that. So we're going to do a research design that goes like this. We're randomly going to select J schools from the population of schools of interest. That might be some number like 100 maybe. And then for each of the selected schools that we drew in the first step, we're going to randomly draw n sub j students from that school. Let's say it doesn't have to be the same for every school, but let's say that's like 20. And so we have 100 schools, 20 students from each of those 100 schools. So we have a total sample size of 2,000. And we're going to collect data on those 2,000 students. We'll give them some tests. We'll ask them about their socioeconomic status and how much they study and things like that to try to estimate something about how useful some aspect of the education process is for their education. But if someone were to come along and try to replicate our study, do the same process, but do it again, not with our data, but with fresh data, they would have to redraw the J schools. Could still be 100, it could be a different number, but it's going to be different realizations of schools and, you know, different realizations of students within those schools. So a very different type of research design might be to, you know, first select the schools, then select students, give them some tests, and then next year go back to the same schools, get new students, give them tests. So the schools would remain the same, but the students would differ every year as, you know, more students graduate. But what we're talking about now is when, if you try to replicate this study, both the schools that you take students from and the students from within those schools that are drawn are going to be random. And so if you tried to replicate this, both the schools and the students would change. So how might we think about a generative process for something like this? We might first have this positive random variable tau, which basically captures the standard deviation in the intercept from one school to the next. So tau is some realization of exponential with rate r sub tau. And then we have alpha j. These are going to be our intercepts. And so we have indexed by j. There's one of them per school. So some schools are better than others, and consequently they have different overall average behavior that is captured by these alpha j intercepts. Then we have a coefficient beta, which is going to be common to all schools, and it has a normal prior. The prior on alpha is normal 0 with standard deviation tau, and we want to estimate tau along with the alphas and the betas and everything else. We have a standard deviation of the errors. Let's say it comes from an exponential distribution, and then we use that as part of a normal distribution for the errors and, you know, how well they do on some test or something. That's what y is. And formed by this school-specific intercept alpha j multiplied by, or plus beta, which is common to all schools. It doesn't have a subscript. Multiplied by the class size of the student plus the error term epsilon that applies to student I in school j. So we might be interested in estimating the sensitivity of test scores to the size of the class that the student is in, allowing for the fact that some schools are just randomly better than others for reasons that we're not modeling, and that's going to be captured by this alpha j, which is a more general setup than assuming that there's a common alpha that just pertains to all schools equally. That's, you know, not something that seems to make a whole lot of sense, particularly if you're mixing, you know, private schools and public schools as part of the same data set, or, you know, something like that. So, questions about this setup? Yes.
Sorry, but what do the 3 equals mean?
Oh, that just means it's defined that way.
Okay.
You can just think of it as 2 equals.
Okay.
Other questions?
Hi. Do you have a certain systematic where how to start writing up such a model? So why do you start with a standard deviation of the intercept when you, for your different parameters? Or do you have a systematic approach how you start up writing such a model?
Yeah, so there's no real order to these conceptually. So it's really just defining a joint distribution over all these parameters. When you're writing this with Stan, which is what we're going to do next, you have to take care to, not do some things, out of order and use a variable that hasn't been defined yet. Otherwise, you'll get an error message. But just when we're writing this in terms of math, no, the order doesn't matter. We tend to, some people write, starting with the data, and then, so they would start with y, and then they would define what alpha and beta are. You'll see that a lot in books. But I like to put the data last. But anyway, it's just a convention. No hugely important meaning behind it. Okay. So, as promised, all right, so we want to write a function in the functions block of a Stan program that's going to output a vector, which is our predictions for y. And so this is our prior predictive distribution for y, what we think the distribution of test scores is going to be. And so when we write a function like that, it needs to end in underscore RNG to tell Stan this function is going to be drawing from various random number generators when it does that. In order to, for this function to do its thing, it's going to need to take in an integer j, which is the number of schools, an integer array of size j, which we'll call n. That's the number of students in each school, but let's just assume that's like 20 for all of them. But anyway, our function is general enough. It could allow, some schools to have more students selected into this study than others. Next, we're going to have a vector called class size. So for each student, we're going to have some number for the number of students in their class. So that's going to be basically our x variable. And then we have hyperparameter values for each of these unknowns. So our tau, you're going to have to choose a number for that. Our sigma, choose a number for that. The rate parameter for the standard deviation of the errors, in addition to your mean and standard deviation and your normal prior for beta, which is the coefficient on class size. But anyway, your function is going to take all those numbers. Doesn't particularly matter what they are. For the purpose of this exercise, we want to think about how we would take those inputs to the function and then use random number generation, use just combining the things together in a way that's consistent with this data generating process. In particular, the part about each school gets its own intercept, being drawn from a normal distribution with standard deviation tau. So first we're going to have to draw tau somehow, exponential. And then, like with loops and stuff, we're going to want to make a school-specific intercept and then combine that with everything else to get what we predict y to be before we see the data on y. And this is going to be a way to draw from our so-called prior predictive distribution, which is very important from a Bayesian perspective. We can always use that to assess whether our priors seem reasonable. But in order to do that, we first have to come up with a function that's going to draw from that distribution, which is going to be a several-step process that's sort of illustrated here in math. But what we want you all to do is to write sort of the body of a function in the Stan language that starts like this, that has that signature and returns a vector of predictions on y. Go. Yes, question.
Maybe you said this. Is the mean of y forced to be zero? Is this model specified? Don't you need alpha 0 or alpha j's to be?
Yes. So the question is the mean of y forced to be 0 here? So we're saying that each of the, wait, why am I talking into this? We're saying each of the alpha j's is being drawn from a distribution that has mean 0. But if you took the mean of those j things, it wouldn't necessarily come out to be exactly 0. It could be a little close to 0. It could be far from 0. Whether it's probably close to 0 or probably far from 0 depends on how big tau is. And so we want to estimate that along with everything else. And so this setup does allow for the fact that these could change. But then again, the intercept, you would interpret that as, well, for a class of size 0, which I don't know how well the students in a class of size 0 would do. That's kind of a metaphysical question. Anyway, write the STAN program. Again, the point here is not to write like the perfect STAN function right on the first try, but just to give yourself a, make a start on it, see how you might approach something like this. So, corresponding to the previous slide, we're going to take a realization of tau from an exponential distribution, so exponential underscore RNG. We're going to get a realization of sigma, standard deviation of the errors and test scores, also from an exponential RNG, but with a different rate parameter, R sigma. And then we have our normal prior for beta, the coefficient on the class size, which we're going to take from a normal RNG with mean mu beta and standard deviation sigma beta. So those are our priors for the common parameters, tau, sigma, and beta. Then we're going to declare y. We'll fill it in later, but we're going to declare y to be a vector of size, I don't know what, but it's the sum of the integer array given by n, all the students in the whole study. And then we're going to declare this integer called pos for position, initialize it to 1, and we're just going to use pos to keep track of where we are in the loop. So the loop, it's actually two loops, an outer loop over schools and an inner loop over students within that school. And the outer loop goes from 1 to j. Again, j is the number of schools. Inside that loop, we're first going to obtain a realization of alpha j from a normal distribution with mean 0 and standard deviation tau. And we've already obtained our realization of tau outside the loop. Then we're going to take that realization of the intercept and use it in our inner loop for I, the students in school J. So there's going to be 1 to n bracket J students in the J school. And then inside the inner loop, we're going to create mu, which is equal to alpha j plus the coefficient beta that we've already obtained a realization of, multiplied by the class size of the student in that position, starting with 1, and then we're going to increment pos as we go. We'll take a draw from the error distribution for epsilon. Again, that's from a normal, now with a standard deviation sigma. We add mu, which is the signal to the noise, epsilon, and we get a realization of y, that student's performance on the test or whatever indicator we want. And then we stick that in the position that we are in the loop for y. We make position 1 more, and we go to the next increment of the inner loop. When we're done with all the students in the first school, then we jump back to the top with the outer loop, and we do the second school, and then all the students in the second school. They'll have a different value of alpha j for the second school, the third school, etc., through all the schools, all the students within the school, jump out of the double loop, and then we return y, which has now been completely filled in at the last step, and it goes into the outside. And so that's one realization of a vector of prior predictions for the outcomes for all these students in all these schools. Questions about that? Oh boy. Coming soon. Yes. So it would be a little bit more convenient if you could make more than one draw at a time. Ben Bales has been working diligently on that for a number of months, and I think it's almost ready. But that doesn't change the concept. Yes? Oh, you need this thing.
Is there any reason why we, for instance, define alpha j, or like variables? Could we, no, maybe alpha j makes sense, but mu, maybe we could just get rid of mu and just directly plug it in, or is this just, is then?
Yes, so I've done this in a rather verbose way. You could combine, y pos is equal to mu plus epsilon. You could collapse the inner loop to just like that line and do the normal draws within it and stuff like that. So your inner loop, it could be just be 2 lines. But I verbose to try to make really clear what's going on. Yes?
In the inner loop, you have this real mu, real epsilon. Does it mean you create these variables each time you loop over them? Yeah.
Yes. So if we were doing a Stan model to try to estimate these things, it would be possible to estimate the posterior distribution of any of these. Now, if we were doing this with actual data, we wouldn't be drawing y, we would have data on y. And so we would have to estimate beta and all the alphas and the tau and all that stuff in order to give us a model of y. And then the difference between y and its predictions is our posterior distribution for epsilon. So yeah, we could easily estimate a model like this, but before we get into estimation, you have to be very clear, very explicit on what your model for the data generating process is. Once you do that, then you just need to change a few things and you're ready to estimate it. But a lot of the work that you have to do goes into thinking about all the different parts of the model, how they fit together, and doing this, looking at the prior predictive distribution, seeing if it makes sense before you even go to try estimating the parameters for a model like this. And that is true for any Bayesian analysis. It's especially true for any hierarchical model that's more complicated than bowling. Because there's, even on this slide, which is just like one slide, there's a lot of parts that are going into it, and you have to think how those parts fit together. But, if you think about it, this is just kind of like bowling with more than 2 steps. It's like 6 steps or something like that, but, first get tau, then get alpha j, then get mu, then add on epsilon to that, and that's your prediction for the outcome for that student in that school. Yes?
Thank you. So a syntax question. On the, you always write normal underscore RNG. In the last session we saw the tilde notation. Is it exchangeable or is there a difference between the two?
So this, here, you can basically understand this in words as tau is drawn randomly from an exponential distribution with rate r. That corresponds to this syntax in Stan, but in Stan code, when we wrote out the model block for the interaction terms before, and someone asked why don't you use the tilde syntax? The tilde in Stan should not be read as, this is drawn from that distribution. Because that's not exactly what Stan is doing when you go to estimate one of these things. It does mean that way in bugs, and that's why we started out with it, but then we sort of regretted that choice because it was causing too much confusion, and that's why I tend to prefer the target plus equal is to make it clear, we're just adding another log PDF or log PMF onto this thing, and that defines a distribution that Stan can draw from when it's doing its MCMC algorithm. So as far as this is concerned, you can understand the tildes as implying draw from this RNG. But that's why I don't like to use tildes in a model block of a Stan program, because it doesn't exactly mean that unless you sort of interpret your Stan code as saying this is what I think before the data are observed. Okay, making good time. Okay, so if you took this thing, and I have a copy of that, it'll end up on the website at some point, and you put that in a program called schools.stan, you called expose stan functions, which is a function in the rstan package, it would compile just that function, and then it would make it exposed in the R's global environment. And so you can see its arguments is the same as the arguments that were we specified in our function. You can actually call that function from R. And you would get a realization of the prior predictive distribution, this vector for all the students. And doing that, like I said, and doing it repeatedly to draw, you know, throughout the prior predictive distribution instead of just getting one realization is a really good way to judge whether your priors make sense, whether your R tau is reasonable. And oftentimes when you do this, you'll get predictions that are just way too wide. Like, you know, predicting some student gets like a 4% or something like that on the exam, which, you know, doesn't really make a lot of, there's not going to be a lot of people who get like a 4% on the exam if they actually show up. So a lot of times when you do this, you find that your predictions are just way too wide to make sense, in which case you need to be using probably tighter priors in order to get something that seems more reasonable. But you can do all of this by defining functions in the functions block of a STAN program, exposing them to R, and from question. I didn't understand. Okay.
Thanks. My question is about the seed, because if the seed is 0 in the argument, then each time you call it, it will give you the same reply, right? So you need to pass it on a random number from R, or am I missing something?
This seed is really just the initial seed that it makes to initialize the random number generator. Mm-hmm. So if you called it multiple times, you're going to get different draws each time. If you called it, recompiled it, called it again, you would get the same draws as what you did before. So it is possible to make this reproducible, but it behaves the same way R's random number generator. It is initiated to something. R's is initiated based on the time of the day, which is kind of arbitrary. But anyway, Stan, the way we have it here, it's initialized with a seed 0. Anyway, if you draw from the function, you're going to get random numbers, and they're perfectly good for sort of evaluating whether your predictions make sense, which is really the point of writing a function like this. But good question.
Thank you.
Right. You okay? So we've talked a lot about hierarchical models without really formally defining what they are. So let's do that now. Hierarchical model is a model where the prior for some parameter is specified to be conditional on another unknown parameter. And like I said before, these hierarchical models are often used in situations to allow the parameters to vary from one group to the next. So the parameters from one school can be a little bit different or a lot different than the parameters from another school. Whether there's a lot of difference or just a little bit of difference is something that we want to estimate. So we want to estimate that tau in addition to all of the alpha j's. And you can think about this, you know, hierarchical structures like this. With group structure, you know, there's some likelihood contribution for the jth group, the jth school. There's priors over how the parameters from one school differ from the parameters in another school. And then there's going to be priors on the parameters that are common to all groups, to all schools, like the beta for the class size, or the sigma, or the tau. These things common to all schools, they don't have an index, but alpha j is specific to the jth school. So we have different types of parameters. We have local parameters, we have global parameters, and we need priors on all of these things. And even more so than a not hierarchical model, where the priors are usually not going to matter that much. In a hierarchical model, the priors take on more importance because you have, you're estimating a more ambitious model. You're estimating parameters for each school, maybe estimating parameters for each classroom in each school. So you're estimating a more ambitious model. And even though you may have a lot of observations, you might not have a lot of information on some schools. Maybe some schools only have like 8 people that are drawn to be part of the study in them. So you're not going to get a lot of information about every single group necessarily. And in a situation like that, priors take on more importance, particularly the priors that express your beliefs as to how much similarity or how much heterogeneity there is, or there you think there is before seeing the data in this data generating process, before you actually observe the data. And so the priors that sort of capture the group-to-group variation are very important in a hierarchical model like this. In R, the most common way to estimate hierarchical models from a frequentist perspective is to use the LME4 package. And in their vignette, they have a table like this, which says all sorts of little pieces of syntax that you can specify for the likelihood in a hierarchical model. That basically boils down to you have some parentheses, and then you have something to the left of a vertical bar, and you have something to the right of a vertical bar. The thing to the left is the variable whose parameters, whether it's a slope or intercept, whatever it may be, you're allowing to vary. The thing on the right of the vertical bar is a factor, a categorical variable, G, generically. It doesn't have to be called G, but anyway, it's some factor indicating the grouping structure. So who's in what school? And it's going to estimate a parameter, depending on how you specify these things, for each of the levels in your grouping factor G. And you can have multiple grouping factors, all sorts of complications, but they're built up from little pieces like this. And the LME4 parser, the parser in the LME4 package, what it does, it takes statements like, X, where X could be class size, and then it's saying the coefficient and the slope are on class size can vary from one level of G to the next, where G would be like schools. And it basically converts statements like that into a sparse matrix, which we'll call Z, that is basically just the interaction between some of your variables, which would be an X, like class size. But if you interact those variables with the school dummy variables and put all those in the columns of a matrix called Z, that's what Z is. And so Z basically contains all these interactions between the predictor and the grouping structure. But other than that, it's just like any other predictor with that column of Z. Anyway, you can specify hierarchical models with LME4 syntax using these little expressions in parentheses that you add on to the rest of your formula. And we'll see an example of that in a second. But are most people kind of familiar with LME4 R package? Sort of heard of it before. A lot of people have. Anyway, it's very similar to, there's a SAS routine that does stuff like this, data, all sorts of things for estimating these models. Okay, here's the slide with the most math on it. So in these hierarchical models, in general, we're going to allow both the intercepts and the slopes to vary from one group to the next, from one school to the next. And so if we say beta j is this coefficient on some variable that's specific to the j school, we want to write that as beta overall plus b sub j. So in this expression here, we have, beta j, the coefficient for the j school, is equal to some common part beta for all schools, and a deviation from that common part in the jth school, and that deviation is captured by b indexed by j. And then we take all of these b's, which can be a vector, and we concatenate them into a really long vector, over all our j schools. And so then we can write our expression for the outcome using matrix algebra. We can interpret it in two different ways, depending on whether we're taking a Bayesian approach or a frequentist approach. So, y is equal to x times the common betas, the vector of common betas corresponding to each of those columns in x, plus z post multiplied by b. So x times beta captures all the common variation with the common coefficients beta, and z times b captures all the heterogeneity from one school to the next in the columns of z that are being multiplied by their respective. Of course, there's an error that is added on to that. Now, just because we can write this doesn't mean that the interpretations of it are going to be the same depending on whether we're Bayesian approach or frequentist approach. So if we take a Bayesian approach, then the mean, our expectation of y is equal to the sum of these two things, x times beta plus z post multiplied by b. But the frequentists take a different perspective on this. Only x times beta is part of the conditional expectation of y, and z times b is actually part of the error term. So from a Bayesian perspective, the only part of the error term is epsilon, but frequentists sort of group this whole thing along with epsilon to be an overall error term. And b in the LME4 approach is itself decomposed into this product of L, which is a Cholesky factor of the covariance matrix and the multivariate normal prior or assumption for the B's, multiplied by U, which are independent standard normal, multiplied by sigma, which is the standard deviation of the epsilons. So all that complication that came from LME4. But that is just a little bit of a way of illustrating why frequentists take a different perspective on these hierarchical models versus the Bayesian one, which frankly makes more sense. Okay, we'll condition on x and we'll condition on z, estimate all those parameters jointly, get their posterior distribution. And so for Bayesians, you have this multivariate normal, or it doesn't have to be multivariate normal, you could choose a different prior, but let's just say multivariate normal prior on the B's means 0 because they're deviations, and they have some structured covariance matrix sigma, which can itself be a hierarchical function of parameters theta, and then y is normal conditional on x times beta plus z times b with a diagonal error matrix. But for the frequentists, they say, well, these b's are not really parameters. They're part of the error term. They analytically integrate those out of the likelihood function when everything is normal. Then they get a new function, which they call the real likelihood function, and they choose the common parameters, the betas, the sigmas, etc., to maximize that multivariate normal likelihood, whose mean is just x times beta, because they've already integrated the b's out, and it has a different covariance matrix, which is dense. And so among the reasons why the frequentist approach to these hierarchical models are confusing is you don't actually get like standard errors or p-values or anything like that for the b's, because the b's are technically not estimated. They would change if you tried to replicate the study over and over and over again, so you don't have a sampling distribution for those b's. And so really you only have point predictions rather than estimates that come from manipulating the residuals in a model like that. So I really don't want to get too hung up on the differences between the frequentist and the Bayesian interpretation of these models. Obviously, if you're doing it in Stan, you could do it either way, but presumably you're going to want to use the MCMC approach in Stan, and so we'll be sort of taking the Bayesian perspective, conditional on X and conditional on Z, and we'll estimate the betas along with the B's and everything else. But I did just want to highlight a little bit that you can have different interpretations of the parameters, even if you write it the same, depending on whether you take a frequentist or Bayesian perspective. So last 10 minutes or so of this session, want to get into rstanarm. So rstanarm and brms, which we'll talk about brms when we come back from the coffee break, are our packages that accept the same syntax as LME4, but they use Stan and in particular MCMC to estimate the parameters of the model, the posterior distribution, using the Bayesian perspective. Also, rstanarm and brms also adopt the syntax for specifying splines that is introduced in the MGCV package, which comes with R, to estimate smooth but not necessarily linear functions of these predictors. And so rstanarm and brms allow you to specify priors on all these parameters, so those are additional arguments to specify, but they usually are going to have defaults. And so you can use rstanarm or brms first to make sure that your data are amenable to the hierarchical model you're doing before you start trying to tweak things and estimate your own model using Stan. And so this is a pretty good preliminary step. And so the example that I want to use comes from Richard's book. This is an example involving tadpoles that live in tanks, like fish tanks. And so the question we're going to ask is, do the tadpoles in all these various tanks survive to the end of the study, or do they die? And so there might be reason to think that there's going to be systematic variation in the survival rate of the tadpoles from one tank to the next. So if one tank gets contaminated, then probably all the tadpoles, or most of them, are going to die, versus uncontaminated tanks. There's probably going to be a higher survival rate, things like that. So there's plenty of reason to think that the survival rate is going to vary from one tank to the next. It also might systematically vary by the size of the tank. In this case, size is just a factor. There's big tanks and small tanks that are indicated by these size variables. So the first few lines there, they're important. They just download the data, but there's no real conceptual thing going on. Each row of that data set is a tank, corresponds to a tank of tadpoles, and so we want to make that into a factor which specifies the group structure for these data. And then we use the stan_glimmer function in the rstanarm package to estimate a binomial model for how many of the tadpoles in each tank survive as a function of the size of the tank and intercept that varies from one tank to the next, which we specify with this piece of LME4 syntax, parentheses 1 vertical bar tank. That is saying allow the intercept to vary from one tank to the next. We specify family equal logit to use a logistic inverse link function in this binomial model. We call that, it's already comes compiled from CRAN when you install the rstanarm package, so you don't have to recompile this model, and it pretty quickly estimates a posterior distribution that has 51 dimensions to it. So where did all these dimensions to our posterior distribution come from? Well, 48 of them are these tank-specific intercepts. There's 48 fish tanks in the data set, and then there's 3 additional parameters or 2 or 3, something like that, additional parameters to estimate an overall intercept, a coefficient on the size variable, and the tau, the standard deviation, and the intercepts from one tank to the next. So 48 tanks, 3 common parameters. That gets you to a posterior distribution that has 51 dimensions to it, and we estimate 4 chains keep 1,000 draws per chain, so we get 4,000 draws from each of these 51 parameters. They come from Stan, so these are like really good draws from the posterior distribution, but we use the convenient, or at least conventional, LME4 syntax to specify this model. So then if we go to look at the output of it, so this, when you call like print, we can see the posterior median of the overall intercept is like 1.2. The standard deviation of the overall intercept is like 0.4 or so. These are just summaries of our posterior distribution. The coefficient on the size of the tank seems to be not that large relative to the uncertainty in it. But when we look at this 1.7 corresponds to the posterior mean of tau. How much do the intercepts for the survival probability vary from one tank to the next? And so if this was close to 0, we would basically be saying there's not a whole lot of heterogeneity here. You know, fish tanks are fish tanks, and you know, tadpoles either survive or they don't. But since this is, you know, reasonably far away from 0, closer to 2, it is actually saying that there's a lot of commonality in the outcomes for the tadpoles in the same tank, and tanks are, you know, differ from each other in non-trivial ways. Like I said, if one tank gets contaminated, or you know, its temperature is too hot or too cold or something like that, you might expect more of the tadpoles in that tank to die compared to like the average tank. And so this posterior distribution for tau, it has a mean of like 1.7, is saying, you know, there's something going on here that we should be paying attention to if we're interested in tadpoles. So that's kind of the summary output of rstanarm. Also with rstanarm, and to a large extent brms2, we define methods that are the same names as the methods defined in the LME4 package, even if we sort of interpret those maybe in a little different ways. So LME4 defines a method called fixef, F-I-X-E-F, to extract the so-called fixed effects, which is sort of the frequentest term for the parameters that are common across all groups, in this case tanks. And so we have a common intercept and a common coefficient for the size of the tanks. And so even though, you know, we usually say common parameters rather than fixed parameters, we can still extract the posterior medians of those things from the output of our posterior distribution that we obtain from Stan_Glimmer. We can also use the ranf function to extract the posterior medians of all the alpha j's, which correspond to the so-called random effects from the frequentist way of looking at it implemented in LME4. And like I said before, 48 tanks of tadpoles, 1 intercept per tank that we are estimating. And if you add the fixef part to the ranf part, you get what is returned by coef, which is basically returning the what you would call the intercept for, you know, each of these tanks. And the intercept for each tank consists of the common part plus the deviation for that tank. And so the common part is the same, but each tank has a different deviation. You add those two things together, and you get your posterior beliefs about, you know, this or that tank, and we can, you know, extract the posterior medians on those. But like with everything in Stan, you know, the raw draws are available for you to do whatever you want with them. If you just do like as.matrix, as.dataframe, you get just all of the draws, and you can do anything. You can pass those to base plot. You can pass post to shiny stan. So you can do all these things that you would do in some cases, like with posterior predictions, even more things with the models that come out of our StanArm, whether those are hierarchical models or non-hierarchical models. So that is my last slide for this session. Are there any questions about the tadpole example before we break for coffee? I'm not going to be able to throw it that far, but I can throw it to you.
Okay. You mentioned that 1.7, the standard deviation, is a bit much, and that's when we know that there's a tank effect. But how do you decide what is too much?
Yeah.
Standard deviation.
Yeah, I'm not a biologist, so what may seem like a lot to me may seem like not a lot to you. I could look at the whole, so this is just the posterior mean. I could look at the whole posterior distribution to see, how much mass there is near zero. But what I do know is if it were exactly zero, then it would be telling me I don't need a hierarchical model. All the tanks are fundamentally the same. But, if it's away from zero at least a little bit, it's telling me it was a good thing I estimated a hierarchical model that allowed the intercept to vary from one tank to the next, because probably the water temperature or the algae or something like that for some tanks had an adverse effect on the tadpoles in that one, and I needed my model to capture that variation. Yes?
If you have non-ignorable missing value with the example, would you introduce a new random variable, or would you make some other ways to deal with it?
So the question was about missing data, which is something that is going to be too advanced really for us to get into even with our additional hour and a half after. But you can think of missing data in a Bayesian context as another part of a hierarchical model. So the missing values are going to be parameters that you declare in your parameters block. There's going to be proposals for those, and you want to stick those proposals in along with the rest of the data that were observed in order to get a likelihood for the outcome, specify a prior on the missing, maybe specify part of the model where you're modeling the missingness mechanism rather than assuming it's ignorable, etc. So it does really fall under the heading of hierarchical models, and you can do a little bit of that with BRMS, but that is something that oftentimes if you're dealing with missing data, you're going to be wanting to write your own STAN programs that sort of convey what you do know about the process by which some observations become missing and others are observed. Other questions? I know there was one in the back somewhere.
Mine is a very simple one. I guess I'm missing something big here. But like with these two packages that you said, BRMS and the other one that kind of uses the same syntax, don't we have to, at some point, specify priors, or do they have some embedded, like default priors?
Yes. So in our StanArm, all of the priors have some default values that you can certainly change. So if you look at the arguments for stan_glimmer, there's going to be prior and prior intercept and things like that. They have default values, but you can specify them. It's more or less the same thing with BRMS. There's a little bit of a different syntax for that because BRMS, which we'll talk about after the break, actually builds a STAN program locally and compiles it. So it really just injects little pieces of STAN syntax for your priors. But anyway, you can look at what the default priors are for a particular model with BRMS. You can change those if you want. But really, I think what we're mostly trying to get, we'll get a little bit toward the end of the second session, but to just sort of think about the hierarchical structure to data and to data generating processes, but really thinking about what priors to specify in a particular situation is going to depend on what you're studying. And so I don't know if there's too much point in dwelling on that in a tutorial like this, but you can change them. Hopefully the default ones are not horrible. And usually they're not. Like have not had to change the default priors since like the first version of rstanarm. So that's good. Yes?
Is there a way to see the StanCon behind this?
Yeah. Yes. Easiest way is to just look at it on GitHub. For rstanarm, the models the syntax is very complicated because we try to write like 5 or 6 Stan programs that do like everything anybody could ever want to do with one of these. Even in any particular situation, you may only be using like 10% of that or something like that. So the Stan programs that are part of rstanarm, it's an open source package, like you can seed them. But it's not great for learning. What we'll see after we come back from the break, brms, it just generates code that's specific to the model and the data that you're estimating. It's a little bit better for reading through it and trying to learn about some of these techniques. Another question? Oh, okay. Yes, so these data, the time is not explicitly, it's just has the tadpole died by the end rather than keeping track every hour are the tadpoles alive. But certainly if you had data like that, you could model that with hierarchical structures. And one of the really, I think, cool things about thinking about time series structures is you can allow the parameters to vary over time with a hierarchical process, just like you can allow the data. So most people probably know about like autoregressive 1 structures for data, where like, you know, whatever phenomenon you're trying to model today is only randomly different from where it was yesterday, like a random walk for data. But you can also have random walk for parameters. So the coefficient on something today can change, but it's probably only randomly differently and not very much different from what it was yesterday. Maybe it's a lot different, but we can estimate how much is a lot or how much is a little by estimating that tau for that parameter as it evolves over time. And so really once you start thinking about hierarchical structures and thinking about conditional distributions of today conditional on yesterday, you can apply those ideas to data or to unknown parameters. And in Stan, there's not really a fundamental distinction in the syntax for any of those. It's just we observe data and we don't observe parameters. But once we observe data, we can estimate the posterior distribution of all those parameters under whatever hierarchical structure we think is reasonable in that data generating process. So yes, you can do that. Another question?
Thank you. Related to that, if I want to have this kind of time series and hierarchical data, is there a package for it, or do I need to start writing Stan code for myself?
So what I was referring to, I was in my head mostly writing my own Stan code for something like that. There is a R package called Walker, W-A-L-K-E-R, which, like rstanarm, comes with some Stan models already precompiled. Unlike rstanarm, it has this time varying conditional distributions on parameters. So you can look at the vignette in the documentation of that, and it might get you started for writing your own Stan model. Okay, so I think we have 30 minutes for coffee, something like that. Come back, same room. talk about BRMS. We'll talk about writing our own Stan programs, etc.